Welcome back, everyone. So, today we're going to start a new series on recursion. And just like the series on reduce, we're going to try to build some intuition for it and hopefully move right along. So, I'm going to assume about you that you at least have a basic understanding of JavaScript and especially ES6, and that you want to learn. And, well, that's basically it. So, definitions are tricky, right? So, words can have different definitions depending on the context. I'm going to try my best to keep everything as simple as possible, just so I'm not overloading you. I know how confusing it is, especially if you're a beginner. If you're more seasoned and you're reading this or listening to this, you may have your own ideas about what I'm saying. But if you're a beginner, don't be confused or scared by some of the big terms. I'm going to try to keep it as simple as possible. Okay. So, simply stated, recursion involves when a function calls itself. Right? It's a bit tricky, but when a function calls itself, and there is a bit more to that because there's also some other scary terms. There's co-recursion, indirect versus direct recursion, trampolining. A function can call itself that then calls, or call a function that then calls itself again, and that's slightly different. But the idea is that a function is going to call itself at some point. But why? Well, certain problems lend themselves to recursion. So if you have a problem that, when broken down into subproblems, if those subproblems look like the main problem, you're probably looking at a recursive solution or something that can be handled with recursion. It can be a more elegant solution, and it involves less steps most of the time. But you can think about recursion as, if someone asked you like like how to eat a burrito, right? They'd be like, how do you start? And you'd be like, what are you talking about? Just take a bite. Like, yeah. But after that, you'd be like, what are you talking about? Just keep biting the burrito. If you know how to eat the beginning of the burrito, you know how to eat the end. So just keep taking bites. You know how to solve that problem, right? So that's my crappy example for recursion. So that brings us to this big blob of code. Now, you don't have to know what's happening here. I want you to look at the shape of the code on both sides. And if you notice, the left-hand side here is more condensed. Right? There's less steps. And on the right-hand side, it's got quite a bit going on. Right? There's more moving parts. And both of these are solving the same problem. So they're both solving the same problem, but one is markedly different than the other. It's a lot shorter. And on the right hand side, in this iterative solution, you're having to keep track of things that you wouldn't have to keep track of if you use recursion. Right? The JavaScript runtime is going to keep track of your stack frames and stuff. So you don't have to implement that with recursion. Well, why not? Why not use recursion? Well, there can be performance issues with recursion depending on your language of choice. Certain languages aren't optimized to use recursion. You can also have problems that don't lend themselves to recursion. We talked about that just a second ago, right? And also there is a team dynamic element. It can be a stylistic decision, but that can be something as well. So here is the simplest recursive function, right? I've named it run forever. Guess what that does? And when called, run forever just calls itself. But the question is, when will this function terminate? When will it return? Well, theoretically, never, right? Because we haven't told it to. But practically, it's going to result in a stack overflow. So, your computer only has so much memory, and each function that you call has a stack frame, and it's going to have some associated memory with that. So how can we tell run forever when to stop? Well, we need some condition to know when to return, right? We need some kind of, you handle this with an if statement probably, but we need some condition to know when to return from the function. And often we need some information passed into the function to be able to determine that, right? So, but remember the function calls itself. So if there is any information, you may have to pass that along in the recursion. So let's look at a slightly different example. So this is a function that just will log, a certain number of times. We're calling it with 3 at the bottom. And so it's going to log 3 times, right? Because we told it to. So we're first going to check to see if the parameter is 0, which the first time it's not going to be because, as we said, we called this with 3, right? So 3 is not equal to 0. Well, this is known as the base case. It says when the recursion should stop. So the condition that says when we should return from our recursive function, that's called the base case. And then it's going to log the input. And then any code that isn't the base case or the recursion is called the action. And sometimes it's kind of nebulous, but that's the way I like to think of it. Then it will call itself. But notice that we're decrementing the input so that it doesn't run forever, right? If we just passed in 3 every time, we would never hit our base case, right? Because 3 would be equal to 3. It's never going to be equal to 0, so we would never return from the function. And the function calling itself is the recursion. Note that we're returning the result of the recursion. When we return the result of the recursive call, we're in what's called the tail position. So we're not really going to talk about that too much, but just know that it's not necessary for you to actually return the result of the recursion. It really depends on the problem, but we'll cover that in another video. But eventually, if we keep decrementing this number, we're going to call this function with 0, and the recursion is going to terminate. So we will hit our base case. And that brings us to 3 terms. The base case, the action, and the recursion, or the acronym BAR. I don't know if I've seen this anywhere, but it seemed evident to me. I'm sure somebody else has come up with it, but this is how I remember recursion, and I just kind of keep it in the back of my mind. So let's look at another example. This is an add function. Obviously, it takes a list of numbers, and we're just going to sum them up. So we have this accumulator here, which we start at 0. And we're going to build onto this by adding each element in the array to it. So our base case here, the condition that says when we need to stop, right, is we're going to check against the length of the array. When the array is 0, when the length of the array is 0, but there's no more elements in it, well, we have nothing else to add. So we're just going to return the accumulator. And so here's our recursion. Notice we're going to pass in the tail of the array. And by the way, if you don't understand that, the tail of the array would just be everything but the first element, right? So this is important to stop the recursion. If we just kept sending the same array, this here, if we kept sending this array of 1, 2, 3 in, and we never removed anything from it, well, the function would never terminate. We would just keep adding those numbers. Then we're going to pass in the sum of the accumulator in the first element in the array, which is, the accumulator is 0 at this point, and the first element is 1. And so you pass in 1 to the next function call, and that would get added to 2. Now, since we're sending in the tail of the array every time, at some point it's going to be empty, right? We're not going to have any more elements. And then we come to our base case. But notice that we're actually returning something from the base case, and that's the sum of the numbers. It's this accumulator we've been building up. So here's a pop quiz. Try to implement a join function on strings recursively. In fact, you could use the prior add function as sort of a template to think about this. And in doing this, I want you to think about what your base case would be, what your action would be, and what your recursion needs to be. So something like this. We have this join function. It takes a list of strings, and it's going to join them together, and you see the result on the right-hand side. Okay, so let's talk about what we'll cover in future videos. So the first thing is we'll talk about how to determine your bar, the base case, action, and recursion. I find it's not immediately evident how to do that sometimes, and it's just good practice to go over some problems. And a lot of the time, if I don't know how to solve something recursively, I'll do it iteratively first with a loop. That's a hard word for me to say, iteratively. And I'll come back to it if I know that I want a recursive solution. The next thing is dynamic programming. Dynamic programming will, optimize recursive calls. There's a lot of stuff about optimizing recursion by remembering prior results. So it's a bit like, storing like a cache or something, or if you've heard of memoization, it's a bit like that. We'll talk about that stuff in another video. The next thing is co-recursion, or generating data from a seed value. And we'll discuss that a little bit. It's pretty cool stuff. And then the next thing is trampolining, and this is another optimization technique. A lot of languages don't support tail recursion. We kind of talked about that a little bit before, and you don't really need to know what that is necessarily, but because we'll discuss it in trampolining. But just know that we'll cover this, and it's an optimization tactic. So, and that's really it. So hopefully I was able to impart some intuition, and then once you grasp the concept, try to teach it to someone else. I find that that helps me. These videos have been helping me. So if you like this video, give me a thumbs up. I'd like for you to subscribe if you want to do that, and I will see you in the next video. So thanks.